Okay, so let's continue on that's binding energy per nucleon. We know that binding energy is the amount of energy required to disassemble a nucleus. Okay, so of course, by this definition, the bigger the nucleus, the more binding energy it requires to disassemble it, right? So, so how about binding energy per nucleon? Okay, so let's first define what do we mean by nucleon. If you still remember, nucleon means neutron or proton, right? Okay, so that means all the uh, essential particles in a nucleus, they call nucleon. Okay, so in a nucleus, we got neutrons and protons, and so they stick together, and we need to apply binding energy to separate them. All right, so binding energy per nucleon means the binding energy divided by total number of nucleons. And we know that total number of nucleons means the mass number. So that would be the definition, EB over A. Sometimes we use delta E, that's all right. Okay, so why do we need to learn binding energy per nucleon, not just binding energy? Okay, so the thing is, binding energy per nucleon is uh, to determine the stability of a nucleus. Okay, normally the things have larger binding energy per nucleon are stable, are more stable, right? So more stable. Okay, so the stability of a nucleus is not the stability of a nucleus does not depend on its binding energy, but the binding energy per nucleon. Okay, remember that. Okay, right? Okay, why? Because if you try to get some nuclear reaction for a nucleus, okay, the easier ways to do is to get some part of it out of the nucleus. For example, alpha decay and beta decay, right? So some part of it, one very tiny part of it, okay, comes from the nucleus. So actually you don't need to disassemble the whole nucleus to have nuclear reaction. Okay, so that's why binding energy is not a good parameter to measure how stable is a nucleus. Okay, but binding energy per nucleon, that means how much energy shared by each nucleon when it comes to get separated apart. Okay, so that energy is the determining factor for the stability. Okay, so larger binding energy per nucleon means it requires more energy to separate some nucleons from the nucleus. So that's why they are more stable. Okay, let's do some calculation. Again, you are provide mass of proton, mass of neutron, 1U. Okay, so to be consistent with your textbook, I'm going to use 931.6. Okay, find the binding energy. Find the binding energy per nucleon. Alright, so first you need to find the binding energy and then you divide by A, right? Okay, so for example, helium. We know that mass of the nucleus of helium in terms of U is 4.0026. Mass of all nucleons. Okay, how could we calculate this? It should be 2 mass of neutron, so 2 mass of proton plus 2 mass of neutron. Okay, so that means you need to calculate based on the number given above, alright, 2 times mass of proton. Okay, so this number is mass of proton, this is number of mass of neutron. Okay, so plus, okay. Okay, so here you got that's 4.0 U, okay? So you see this number must be greater than the mass of nucleus, because we know that's how binding energy comes, right? Okay, because the mass of all nucleons, that means their constituents mass must be greater than the nucleus mass, alright? And EB, how could we get the EB? Okay, EB is, we use that 4.203 minus 4.006. Okay, so that's U. Okay, for that's EB, you have to use delta M times C square. So that's delta M times C square. Okay, so times C square divided by number of nucleons. There are 4 nucleons, right? Okay. Possibly I need to create a bit more room for my next question. Alright. Okay. So how could we calculate this? Remember that for that's UC square, is this one, right? So when we say 1U equals to this, actually what do we mean is 1UC square equal to this one. Okay? To be more precisely. So 1UC square equal to this one. Okay? So you are going to substitute that 931.6 mega eVolt into UC square. Okay? Okay, so for helium, the binding mass per nucleon is 6.847. Okay, all good. All right, so let's try to do another one. All right, so how about carbon? Okay, for carbon there are six protons, 6 neutrons, right? So the mass of all nucleons would be like, okay, I use another color for the comparison. 6 MP plus 6 Mn, okay? So it becomes 12 U, of course, alright? Okay, so can we calculate the EB, the binding energy? You need to use that 12.9096 minus that's one UC square. Okay, how many of them? There are 12 of them. All right. Okay, so you see the calculation we got, like you can show that the um, nucleon, the binding energy per nucleons are different for helium and for carbon. All right, and so which one is more stable? Okay, you see, the greater the binding energy per nucleon, the more stable the nucleus, right? So in this case, carbon would be more stable than helium. All right, okay. Okay, so I don't have space to calculate for these two. Can you do them as homework? Okay, for these two, please do it as homework and photo them, please, to the folder, to the homework folder. All right, thanks. Okay, let's move on. Lots of calculation here. So actually we will have a binding energy per nucleon. Okay, so that's figure 3.59. Okay, so this figure is quite useful. We are going to use this figure later. Okay, but right now you could see for this figure is about the average binding energy per nucleon. Okay, it's not just the binding energy, but the binding energy per nucleon. And on the horizontal axis is about number of nucleons. That's the number A, the mass number. Okay, so you see when the mass number is very small, that means lighter nucleus. You see that's the binding energy per nucleon increase rapidly. Okay, and they keep increasing up to a certain point, about around nickel or iron, copper, and then they fall again. Okay, so from this figure, which group of nuclei are the most stable group? Okay, so we could see there are three groups of them. Okay, so for this group, they are what we call, okay, these are lighter nuclides, right? Okay, and for this group, what we call heavier nuclides. Okay, so when you compare, okay, of course heavier nuclei seems more stable in terms of binding energy per nucleon. Okay, but they are not the most stable part. The most stable part is for the medium-sized ones here. So for nucleus around here, they are most stable. The most stable nuclei. Okay. So this is very important idea. You see, okay, for lighter nuclei, they are not stable enough. For heavier nuclei, for the heavy part of the spectrum, you see they are not stable, not as stable as the middle part. So the middle part, that means the medium-sized nuclei, they are the most stable. All right. So that's the conclusion. So we see that the graph pick around iron, highest at the nickel, showing that they are very stable nuclei. Heavy nuclei, such as uranium, need to what? Because they are not stable, not stable enough. So they tend to, if they have nuclear reaction, they tend to go to this direction. Go to this direction means what? Means their mass number is going to be reduced, right? Need to reduce their mass to increase their ability, hence they tend to undergo nuclear what? So this term we are going to study later is called fission. Fission means getting smaller. Okay, lighter nuclei need to what? Because they are here, so they are not stable enough. So they tend to move into this direction to move into this direction, you see the mass number must increase, right? So for lighter nuclei, they tend to need to increase their mass to increase stability. Hence, they tend to undergo nuclear fusion. Okay, so we will go to go into details for fission fusion later, but from the meaning of the word itself, it just suggests fission is something that you can split up heavier nuclei, larger nuclei, and fusion means you can combine that's lighter nuclei, smaller nuclei together. The purpose of all these nuclear reactions is to get them into the medium size. Okay, so medium-sized nuclei are most stable because they have the highest binding energy per nucleon. Remember, never say highest binding energy, but highest binding energy per nucleon. So that's very important because binding energy per nucleon determines the stability of the nuclei. All right, good. All right, so okay, let's see this example. Right, so the large picture. Okay, so again, you see the shape of the graph, and you expect that would be the binding energy per nucleon. Okay, and this is mass number. All right, that means A. The diagram is plot of binding energy per nucleon for a number of naturally occurring nuclei against their mass number. Okay, which was correct of the 5 nuclei plotted. Fe is the most unstable. Most unstable. It's highest, yes, but highest means actually is the most stable, right? Normally, when we say something is stable, which is there's a benchmark. The benchmark is 8 megaevo per nucleon. So above 8, we call it stable, otherwise unstable. Okay, so that means Fe is the most stable. Comparing sodium 23, it takes more energy to split aluminium into individual nucleons. Take more energy to split. So for this question, we don't need to look at that graph. That's because that graph is binding energy per nucleon. But for this one, what we need is the binding energy, not binding energy per nucleon, because we need to split. That means disassemble into individual nucleon. That means constituents, right? So of course, larger, bigger nucleus needs more energy, right? So that must be true. Sorry, the first one is wrong. Okay, so and the third, energy is released if uranium split into 2 nuclei of comparable masses. Okay, so if uranium split up, then it goes up the slope, so that means it becomes more stable. So when things becomes more stable, so this one more stable daughter nucleus, right? So if you have more stable daughter nucleus, what does it mean? It means you release energy. Okay, so that's correct. So because when you split up, the size smaller, and the position of uranium suggests when the size becomes smaller, it becomes more stable. All right, and more stable means it has to release energy. Okay, so we need to do this. Calculate the binding energy per nucleon for this nickel 62 is nuclear energy is nuclear mass is 61.9 something U. Okay, comment. Okay, so you need to find the binding energy. So to find the binding energy per nucleon, first you need to find the binding energy, right? Okay. So how could we find the binding energy? You need mass number, you need atomic number, because you need number of proton, number of neutron, etc. Okay. So where do we get the data? Okay. Remember there's a okay. Here's our periodic table. So periodic table, let's find which one is what we call nickel, right? So for nickel is, where is it? Oh, okay, here. So here's nickel. So let me copy it here. Yeah, that's nickel, right? And what do we still need? You need the mass of proton, mass of neutron, and okay, do we have here? No, so we need to go back to our this page, right? So that's page 3 in the same notes. Okay, so you have the mass of proton, mass of neutron. Okay, so that's mass of proton. So that's data from previous table. Mass of neutron. Okay, all these things before you can solve it. Okay, you need to get all this data. Okay, and also possibly because you need to get the energy, you still need to remember that that's the information you need to get from your data book, right? Or formula sheets. But you need to know that you actually uh, uh, you need to find them, right? Otherwise you don't know how to calculate. So there are lots of data, you see, to find the binding energy per nucleon. If in the examination they don't provide you this data with the question, you have to go to the formula sheet or data sheet to get all these things, right? Of course, you need another formula, which is binding energy, or delta E equals delta M times C squared. Okay, and C would be equals okay, sorry, because you got 1U, so that means 1U times C squared. Okay, that's where we had bad habits. But sometimes the book will write like this. It should be 1U C squared, but sometimes the book just write 1U equals. So sometimes I get the wrong impression about this. Okay, so you got 1U C squared, so everything's ready. So you could calculate that number, right? Okay, so let's do it. So how could we get the binding energy first? Okay, so for binding energy, you need to find delta M, all right? Delta M, okay. You need to find number of proton. So number of proton is 28. Got that 28? That's what we call sorry, the Z. Okay, right? So that 28 mass of proton. How many neutrons? So you got 62. So that's what we call A. So that's mass number. So that means you got 62 minus 28 mass of neutron, and then you take away the mass of the nickel, right? Mass of the nickel, 62. Alright, so let me substitute all the numbers. Mass of proton, okay. Mass of neutron minus mass of nickel is given. Right, let's get the delta M. Delta M would be, okay, 0.585 V48U. Okay, so that's mass delta M, and then you are going to calculate that's binding energy. Okay, so remember 1 UC square equivalent to 931.6. Okay, mega evo. Okay, so that will become 543.3 mega evo. Okay, so you need to find the binding energy per nucleon. So use this number divided by number of the nucleon. So there's 62 of them. So you will get what we call 8795 mega evo. Okay, sorry about I'm not going to have plenty of space now. Okay, shift this down a little bit. Okay, so you still need to comment on the stability of the isotope. Okay, so of course that's 8.795. So in our previous charts, whenever it's higher than 8 mega evo is what we call stable, right? So that means since EB over A is greater than, sorry about my handwriting, it is stable. Okay, that's it. All right. Okay, so that's pretty much our so this is the, I think the third time we're calculating the binding energy per nucleon. This time I also teach you how to get the data for the question. You need to know what data do you need. Okay. All right. So that's for you. Okay. As a homework. Okay. Please do the homework. Take the photo and go to homework folder. Alright, thanks. Okay, and sometimes you are going to use the graph to compare stability of oxygen 16 and beryllium 9. Okay, so we might go back to our previous graph. Okay, the graph is over here. Let's see. Okay, so here's the graph. Oh, I cover everything. Make it smaller. Alright. Okay. Right. Okay, so you need to compare oxygen 16 and beryllium 9. Okay. Okay, can we see it? Okay, so where's oxygen? Oh, right here. Okay, so oxygen's right here. So this is oxygen. So it's about 8. So beryllium 9 is around here. Use this color. Sorry, I might use another color. This one. Okay, so beryllium is around 6.5 mega evo per nucleon, and oxygen 16 is around 8. Alright, so compare the stability of the two, of course. Okay, so you just say since oxygen 16 as greater binding energy. Remember, don't just write binding energy. You must write binding energy per nucleon. Then beryllium no, that's 16 is more stable. That's it. Easy, right? Okay, use the same graph to do this one. Again, your term. Okay, your term. Okay, this one. Homework. Photo. Folder. Thanks. Too easy. 12, 13. Okay, so the rest of the notes, they are quite similar. We're going to use the similar tactics to calculate energy in decay. So remember, for in all nuclear transmutations, energy released comes from the mass defect. So you will see mass defect. Okay, and that's energy released is mass defect times c squared. When we express delta M in terms of the unified mass unit, you can convert that delta M into the mass in U, and 1 c squared equals this one, right? And then we therefore can modify the equation into what? Okay, we can modify that into delta E. Okay, delta E equals delta M times this one. Okay, so just simple, just same idea. So that's delta M. You use units U. Okay, then after you change that into U, you just replace that U with 931.6 megaevo. You get the answer, right? Okay, so let's see one question like this. Okay, radium-226 was once used in plants. Okay, so it decays via alpha decay and with a visible glow. Okay, so we can skip that. Hence, this code form. Okay, so that's quite irrelevant. Write an decay equation for this process and use it to determine how much energy is released. Okay, so need to write the equation, calculate the energy released, the isotopic masses for each particle in this equation, mass of this. Okay, so this is not a question about the sample or of a nucleus, and also it's not about comparing binding energy per nucleon. So you are not going to use a mass of proton, mass of neutron, all right? But you need to write the equation. So for the full equation, you need to know the symbol, all right, of radium, okay, and also you need to know that the mass of the daughter nucleus, that's 222. Okay, you need to write that equation. You need to find out what's daughter nucleus. Okay, so you need to find out the relevant isotopes in the periodic table. Okay, and you need to write the equation. Let's find out what are they. So first, radium should start with R. Okay, so which one's radium? Okay, see this? Can you see that? So radian is it's really okay. Ra it should be 226. Oh, and 88. It's not working. Okay, wait a minute. I need to find. Okay, sorry for my confusion. So I finally see RA. Okay, I need to have a better glasses, I think. Right, so that's RA. Oh, okay. Right, that's our periodic table symbol for RA. Okay, so that would be useful. And of course, we know helium's 2,4, right? But anyway, I got that for you in case you don't know how to find it. Helium is right here. You should know that 2,4 is quite easy to find out. Okay, so we got 2, and that's 222. We haven't got it because they only give you the mass number. We don't know the name, so possibly we need to work out the atomic number before we can find it. So first we need to write the decay equation. Okay, so let's write decay equation of that one. So you start with RA. Still remember how to write decay equation? If you don't, go back to around lesson. I think that should be lesson 18 or 19. I don't remember that. Okay, so that should be like this. When you are going to perform a decay, okay, it always goes like, okay, that's alpha, but alpha is helium. So you could write alpha or you could write helium. They're the same. Okay, so one thing is here. So you need to determine what it is, right? So of course, that's unknown. But we know to balance the equation for alpha decay, there must be alpha and the other thing, right? So it should be 86 and should be 222. Okay, let's find out what is 86 and 222. Okay, 86 should be quite close to radian. Okay, 86 is here, radon. Okay, let's see. This one's radon. Okay, so here. So let's write radon. Okay, we got it. Okay, so we got the equation. How much energy is released? How could we find the energy release? Remember, it's always the mass on the left hand side will be greater than the mass on the right hand side because you need to have mass defect. So energy is always released here. So that means the whole process is a mass defect. The loss in mass becomes energy, right? Okay, let's see how could we get the mass defect. Okay, so mass defect delta M equals the mass of alpha plus mass of Rn minus mass of, oh sorry, I should go the other way around, sorry, Ra minus M alpha minus mass of R. Okay, okay, the mass reactance is always greater, right? So that's Ra, that's radian. So the mass of radian is 226. Okay, you have more digits right here. Okay, minus 4.002604. Okay, U minus 2220.0175 U. Alright, and to get that, what you will have is 0.005296 U. Okay, so that will be our delta M. Okay, so how could you calculate that's the energy released? Okay, so remember that UC square is equivalent to 931.6. Okay, 6 mega evolt. All right, so that one you will get the answer. Okay, so that's the energy release. So again, we see you use the mass of the reactants, take away the total mass of the products on the right hand side. So the answer should be positive because the mass of is about mass defect. So if you use correctly the mass of reactant to take away the mass of product, it should be positive, right? Okay, so we got this one done. Okay, let's do another one. Okay, so for this one, you can do it by yourself. Okay, do some homework. Not some homework by now. Okay, so here's the homework. Okay, again, photo, folder. All right, good. Okay, here. So another one, which is negative beta decay. Okay, so for negative beta decay, if you still remember, the decay equation is about one fast moving electron as negative beta and also what we call neutrino, okay, and a daughter nucleus. Okay, thallium, um, 204 decays via beta negative radiation. Write the decay equation for the whole process. Okay, so this is negative beta negative radiation. You need to write the equation for the whole process to determine how much energy is released. So you need to write the equation first and then try to get the how much energy, determine how much energy released. So here are the things. Again, to write the equation, you need to find out in the so-called periodic table. So that's mass number 204. Okay, so what's the atom this time? Okay, can you see that? I think I got it. It should be this one, right? Yes. Okay, so that's thallium. Okay, that's our thallium. Okay, anything we don't know? So electron daughter isotope we don't know yet. Mass of anti-neutrino 0U. Okay, so that means no mass, but you still need to write the equation include this. All right, okay, so let's write the equation. So you know that's TL, and that's 81 204. When that's decay, it becomes beta, that's beta negative, right? So beta negative actually is an electron. Okay, for electron, still remember how to write the mass number, atomic number. Of course, mass number is 0, but atomic number should be -1 because the charge for electrons is -1. All right, plus, okay, anti-electron neutrino, that's the symbol. All right, plus unknown particle. All right, but we know that, so that's the daughter nucleus, but we don't know the daughter nucleus, right? Okay, so you need to balance the equation anyway. So if that's 81, that's -1. So if you want to balance the equation, it should be 82. Okay, and that will be no change in the mass number. Remember that's for the anti-neutrino or neutrino, it always be 0, 0. Okay, so 82 204, what's this? 82. Okay, 82 should be this one. PB, that means lab. Okay, so we got the daughter. All right, so how could we calculate the energy? Again, remember that you need to find delta M first. Okay, delta M. So how could we get the delta M? That's mass defect. So use the total mass of that thallium. Okay, so that's this number. Okay, the number is just too long. I don't want to write it. Okay, okay, and then you. Anyway, I need to write the symbol first. I nearly forgot. Sorry about that. You need to get a mass of thallium. Take away mass of that one. Take away the mass of this one. Take away the mass of PB. Alright, but we know that the first mass is this one. The second mass will be this one. Mass of electron. The third one got no mass, but we still write Cu minus this one, the daughter nucleus, which is this one. Okay, got all the numbers. Okay, so let's see. So when you try to do the whole thing, you get this number. Okay, so it's still positive. That means you're on the right track. Okay, and delta E just equals delta M times C square. Delta M 0.0001899 U C square. Okay, U C square means 931.6 mega eV. Okay, so that will get you to 0.7638 mega eV. Alright, that's for our calculation of energy release in a beta lactic decay. So essentially the same as alpha decay, but you just need to use another formula, right? Okay, another equation, sorry about that. Okay, so that's another beta negative decay energy. Okay, so that's for your homework. Okay, again, homework, photo, folder. Okay, thank you very much. Alright, so, and after that, we got plenty of practice questions. Okay, so if you've tried some of them, you're not quite sure, you can ask me questions in the collaboration area, or you might send them to me as the evidence of your homework. Okay, so because in the end we might assess your commitment to the subjects, and the effort grade, but at least you should do the homework I ask you to do. Okay, at least that's the least I could ask you. And for all those key questions, you will have an answer here. The answer from this textbook is quite reliable, thanks God. Okay, so that's it. Okay, so we just finished lesson 21. That's the end of mass energy equivalence, and the next lesson will be fission and fusion. Then we'll finish up all the chapter of nucleus. Okay, that's it. See you next time.